Hello everyone. In this session, we are going to discuss about AVL trees. What are AVL trees? What are the applications of AVL trees? And how to use AVL trees. What are AVL trees? AVL trees are binary search trees in which the difference between the height of left and right subtree is either -1, 0 or +1. This is the first type of self-balancing binary search tree. How does AVL tree work? Now consider the following keys 10, 20, 30, 40, 50, 60 inserted in the given order in the binary search tree. As you know already, binary search trees are binary trees where the element will be, there is a condition, the element will be inserted, the element will be compared with the root node. If the element is less than the root, then it will be inserted right side. If the element is greater than a root, then the node will be inserted right side, as you know already. Now, these are the keys 10, 20, 30, 40, 50, 60, which are inserted. First 10 will be inserted, then it will be a root node. Then when we insert 20, we'll compare with the root node whether it is less than or greater than. Yes, 20 is greater than 10, so that it will be inserted right side. And 30 also greater than 10 and greater than 20, so that it will be inserted right side of the 20. Next turn 40. 40 is greater than 10, so that it takes right, and it is greater than 20 and greater than 30, so that it will be inserted right side again. Similarly 50 and 60 also. Now the height of the tree grows linearly in size when we insert the keys in increasing order of their values, so that whenever you want to search for an element 60, you have to take n iterations. Thus, the search operation works at order of n. The height of this tree is 6. It takes linear time to search for an element, hence there is no use of binary search tree structure. On the other hand, if the height of the tree is balanced, because it is taking order of n iterations, order of n complexity, if at all, if you want to search for 60 worst cases, because it is completely right skewed, the tree. So if at all, if we are able to balance this tree, we get a better searching time. Let's say if at all, if you have changed the order of this, let's say elements are 30, 40 and 50, 60, 10, 20. Then, so we'll start with 30 and 40 is greater than 30, so that it will be inserted right side, and 50 is greater than 40 right side, and 60, and 10 is less than 30, so that it will be inserted left side, and 20 is less than 30 and greater than 10, so like this it will be inserted. Let's say if you want to search for the element 60, it takes 4 iterations, order of 4, right? If at all, if it is balanced, so that you can decrease the complexity of this. But now the height of tree is 6 and taking more complexity. In order to overcome that problem, we have to balance the tree. For that, we use AVL trees. See, after in the AVL trees, after the insertion, the balance factor of each node is checked. During the path, whenever you insert a new node, we'll check the balance factor. If the node becomes unbalanced, we have to take the rotation. In an AVL tree, rotations are used to maintain the balance after insertion or deletion, anything. the balance factor must be -1 to 1 for all the nodes. Either it must be -1 or 0 or 1, not greater than this. So when this balance is violated, one of the following rotations we have to apply. Now what is balance factor here? We are talking about balance factor. What is balance factor? Balance factor is the difference between the heights of left and right subtrees. That is known as balance factor. So consider this example which I have given here. Now the balance factor of D is there are no right elements for left element and right elements. So 0 left height of left subtree is 0 for this and right subtree also 0. So the balance factor of this node is 0. And coming to B, will be having one left child, but there are no right child. So 1 minus 0. So the balance factor of this is 1. And consider C, the balance factor of C, there are no more left and right child for this. 0 minus 0, left minus right actually. So there are no more left and right child for this. The balance factor is 0 for this. And coming to A, see, A is having two levels. The height of left subtree for A is 1 and 2. This is 1 and 2, right? So 2, left subtree height is 2 and right side subtree is 1. You'll be having only C node 1. So the balance factor of this is 1. Okay, insertion in an AVL tree follows the same basic rules in binary search tree. But whenever you insert a new node, you have to check this balance factor. Okay, same position you have to, like the node, if the element is less than the root node, then it should be inserted left side and greater than should be inserted right side. But for every insertion or deletion, we have to check the balance factor. I hope you understand what is balance factor. Height of left subtree minus height of right subtree. That's it. Now, why it is required? See, the example whatever we have seen is right skewed. In the last example we have seen, this is completely right skewed, right? So in AVL tree, most of the binary search tree operations we use for search, for finding max, min, inserting the elements, delete the elements, takes order of n time, where order of h time, where h is the height of binary search tree. So whenever it is completely right skewed, it takes those many, that much complexity, order of, let's say 6 now. In the last example we have seen, so it takes order of 6. The cost of these operations may become order of n for skewed binary trees. So if we make sure that order of the tree remains order of log n after every insertion, then we can guarantee that upper bound of order of n log n for all these operations. Now this is what exactly why AVL trees are required to reduce the complexity. See, consider this example. We have a binary search tree. Now for every node we have to check the balance factor. It should be -1 or 0 or 1. It should be -1 to 1. That's it. See, for there are no left elements and right element. Height of left subtree is 0 and height of right subtree is 0, so that it is 0. And here it is 0. Similarly, for 5, node 5, only will be having left subtree and no more right side. So 1 minus 0 is 1. Similarly for 11, no left and right. And for 8, the height of 8 left subtree is 2 and right side is 1. So 2 minus 1 equal to 1. Similarly for 17 no more, so 0. And for 18 we'll be having only height is 1 and right side no more elements, 1 minus 0, 1. And for 12, maximum height of this is 1, 2 and 3, right? So 1, 2 and 3. 3 minus left side 3 and right side 1, 2. 3 minus 2, 1. So that all nodes are satisfying the balance factor rule, so that you can say that the given tree is AVL tree. Now consider this example. See, the balance factor of 8 is the maximum height of left subtree is here 2. See, left side, this, if you consider this 2, maximum height you have to consider. See now, 1, 2, 3, 4. So which is maximum? 4 is max. So 4 minus right side only 1. So 4 minus 1 is 3. Now never will say if at all the balance factor should be either minus 1, 0 or 1. Now you are getting 3. So never will say this kind of trees are AVL trees. So now how to make this tree as AVL tree? To reduce the complexity, we have rotations. Whenever the balance factor rule is violating, we have to rotate the array. Few rotations we have to take place. There are in AVL tree, after performing operations like insertion or deletion, we need to check the balance factor of every node in the tree. If every node satisfies the balance factor condition, then we include the operation. Otherwise, we must make it balanced. Whenever the tree becomes imbalanced due to any operation, we use rotations. So there are 4 rotations. Few are single rotations, few are double rotations. Single rotations are LL rotation and RR rotation. Double rotations are LR and RL. So let's discuss these rotations. Let's say in left rotation, every node moves one position to the right of the current position. So let's say you are inserting 1, 2, 3 elements. So whenever first we'll consider this one as root node. Whenever you insert the first node will act as root node. So root node. Then when you insert 2, 2 is greater than 1. It must be inserted right side. Okay, so 2 is inserted right side, and then 3. So when we insert 3, 3 is greater than 1, so it has to go to right side, but there is right side also one more child node, and 3 is greater than 2, so that it will be inserted right side. Now first, when you insert 1, what is the balance factor? There are no more left and right, so the balance factor is 0. So fine, this is okay. But when you insert 2, first there is already one node and 2 is greater than 1, so it will be inserted right side of this. Now you check the balance factor. For the balance factor of 2 is 0, there are no more left and right. Balance factor of 1 is left, there are no more elements. So left minus means 0, minus right side will be having one element, one height, so that it is minus 1. Means yes, it is a AVL tree. When you insert 3 now, so 1, 3 is right side of 2. Now you check the balance factor. No more left elements, minus 0. No left elements, but one right element, 0 minus 1, minus 1, okay. For 1, there are no more left nodes. Height of left subtree is 0, but the height of right subtree is 1, 2. So 0 minus 2, minus 2. So never will call this kind of tree is AVL tree. What we have to do? We have to balance it. How to balance? So whenever the element is right skewed, whenever the tree is right skewed, you have to take LL rotation. To make balance, we use LL rotation. How to do LL rotation? So now see here, which moves nodes one position to left. So this one will be moved to left side and 2 will make it as a root node. This is how we have to take. So 1 left, again 2 L rotations. So 3 as usual. Okay. So this is LL rotation. Now you check the balance factor. There are no more left and right nodes. The balance factor of 1 is 0 and no more left and right for 3. So balance factor of 3 is 0. Balance factor of 1 will be left subtree height is 1, right subtree height is 1, 1 minus 1 you will get 0. Okay. This is what LL rotation. Similarly, RR rotation. If you are inserting 3, 2, 1, you have to follow binary search rules. You have to add balance factor into this. One more rule you have to add for binary search tree. Okay. So whenever you insert 3 as root node, then when you insert 2, left of this and left of this. Now you check the balance factor of this. For 1 it is 0. For 2, because we'll be having one left element, 1 minus 0 is 1. For 3, 2 minus 0. So 2 minus 0 is 2. Now it is not a binary tree, so that you have to apply rotation. Which rotation you have to apply? That rotation is RR rotation we have to apply. So in right rotations, every node moves one position to right. If at all the tree is left skewed, then you have to make RR rotation. 2 times you have to rotate right side. Okay. Then 3 will come right, and 2 again, one more right rotation you have to take, so that you will get this kind of tree. Okay. Now you check the balance factor of this. So balance factor of 2 is left and right is 0 you are getting. Now the tree is balanced. Similarly, right left rotation. The right left rotation, LL 2 times L we will do, left left. RR 2 times R. When RL rotation, single right rotation followed by left rotation. One right and left. Okay. So let's say you are inserting the elements 1, 3, 2. First one will be root node. 3 is right side to this and 2 is left side. Now you check the balance factor. See, for every insertion you have to check. Here we directly I have inserted, but first one will be inserted. Balance factor of 1 is 0. Okay, AVL tree. When you again, then you insert 3. So 3 is right side of 1. So this will be something like this. And then the balance factor of 3 is 0 and the balance factor of 1 is minus 1. Yes, it is an AVL tree. Then when you insert 2, 1, 3, and 2 is left side of 3 because 2 is less than 3. Now the balance factor of 2 is 0, balance factor of 3 is 1, left minus right. Similarly, balance factor of 1 is left side no elements, right side 1, 2 height. So 0 minus 2 minus 2 height. So it is not. Now here it is violating rule, right? Right, left. So whenever it is right and left side, whenever you insert right side, it is left side, it is violating the right side tree, and left side it is violating rule. So simple, you have to take one R rotation, then L rotation. So what you will get, this 2 will goes here, 2 will goes here, and this 1 will be left side. Okay, see. 2 will make it as root node, left side 1 and right side 3. This is RL rotation. Okay. So now it is balanced. And left right rotation similarly. So when you insert 3, 1, 2, the tree will be something like this. It is violating rule here at 3 node. So left and right, when you insert left side and right side, left subtree, and after this right, it is violating rule, so that you have to take LR rotation. LR rotation means it is a sequence of single left followed by the single right. So blindly you can remember this will go here, and all left side, this will be moved, right side. Okay, LR, left and right. So this will be left, this goes left. Now this, it forms like this. Okay, this is LR rotation. Now if at all, if any situation encountered like this, so then we have to make the rotation. Search operation in AVL tree, because it is a balanced tree, first it is a binary search tree, so that initially you can understand whether it will traverse left side or right side, whether you need to follow. Read the search element from the user. compare search element with the, let's say you are searching for, as I said, if your tree is something like this, let's say you are searching for 2. So 2 is key element. Then compare such element with the root element. Is 2 less than 3 or greater than 3? So 2, sorry, here 2, here 3. You are searching for 3. So whether 3 is greater than 2 or less than 2. It is greater than 2, automatically will take right side. So if both are not matched, compare with the search element, the given root node. If both are matched, then given node is found. Otherwise, you take the right traversal. Then again compare with the right subtree until you found. Okay. Until the end of the tree. This is how you can search. And these are the operations you can perform: search, insertion, deletion. Search we have seen already. Then how to insert. So first, as I said, let's say you are trying to insert from 1 to 8. First we'll insert 1, 1 will become a root node. Now the balance factor of 1 is 0, tree is balanced. Then you insert to 2, you have to follow the binary search rules only. Compare with the root node, whether 2 is greater than 1 or less than 1, 2 is greater than 1, so that it takes right side and 2 will be inserted. Then again you find out the balance factor of 2. There are no left elements, right element. Balance factor of 2 is 0. And balance of factor of 1 is no left elements but 1 right element. 0 minus 1 you will get 1. But still it is balanced. Whenever you insert 3, it is completely, see, 3 is greater than 1, greater than 2. So that it places here. Now after every insertion we have to check the balance factor. Okay. Balance factor of 3 is 0, balance factor of 2 is minus 1, and balance factor of 1 is minus 2. So it is completely right skewed. You take a left rotation. So see, after every insertion we have to check the balance factor. If it is violating, then you have to take the rotation. It is right skewed wherever it is not violating the rule. So LL rotation, so that now it is balanced. Insert 4. Whenever you are trying to insert, compare with the root node. 4 is greater than 2, right side. 4 is greater than 3 also, again right side. Check the balance factors. Similarly 5. Whenever you insert 5, the balance factor of 3 is minus 2. Always when it is violating balance factor rule, first you have to set right the child nodes, then you can set root node. Okay. See, here it is. See, here it is violating the rule. First you set this. Okay. So completely right skewed this portion. First rotate here so that you will get 3 will come here, 4 will be here. Now see, the balance factor of this tree is balanced. Check this. Now see here, whenever you insert 6, here it is violating because 2 is greater, 6 is greater than 2, greater than 4, greater than 5. So it is inserted here. But the balance factor of root node is getting 2. So now what you have to do is, because it is right skewed, so you take the rotation, LL rotation. So LL rotation means 2, it will come here, 4 will be here. So all the elements which are left side will go left and right will go right. Okay. Or all the elements which are left to root node will go to, 4 will become root, will go to left side and right will go to right side. See. So this is how you can insert. When you insert 7, again it is violating rule here. So LL rotation. LL rotation means here 6 will be here and 5 will come here and 7 will be here. So you will get this tree. Now when you check the balance factor, it is balanced. When you insert 8, everything is balanced. Okay. So if at all, if it is not, if it is violating the rules, you balance it. So this is how we insert. In an AVL tree, the insertion operation is performed with order of n log n, so that will reduce the complexity. And insert new element into binary search tree. Insertion logic, as we know already. But for after insertion, you have to check the balance factor. balance factor of every node must be 0, 1 or -1. Then only you go for the next operation. Otherwise, if the balance factor of any other node is not this, then it is imbalanced. Perform suitable rotation. Then go for the next operation. Deletion. Similar to insertion, after deleting a node, the deletion operation in AVL tree is similar to deletion operation in binary search. But after every deletion operation, we have to check the balance factor. That's how you can balance suitable if at all if it is becoming imbalanced, then you perform a suitable rotation so that you can make the tree balanced. Thank you. The applications of AVL trees are: it is beneficial in cases like databases where insertions and deletions and searching takes place are not that frequent, but frequently check for the entries. Okay, frequently where you check for the entries, you can use AVL trees. Thank you, everyone.